Hey everybody, welcome back. Our next talk is from Wido, who's a long-standing PMC member and committer in the Apache CloudStack project. Wido is going to be talking today about Ceph and Apache CloudStack. So please everybody give Wido a warm welcome. Over to you, Wido.
Okay, thank you. So indeed, yeah, for who have you been following me for the last few years, I've been very active with Ceph and with CloudStack, and I've given numerous talks about Ceph on Ceph Community Days, on CloudStack Days regarding Ceph and CloudStack, and I wanted to give an update on how we are using Ceph and CloudStack as a combination. So let's go. But for those who don't know me, who am I? I'm Wido den Hollander. I was born in the Netherlands, and I would call myself a Ceph, CloudStack, and IPv6 guru. My current day job is being head of infrastructure at Total Web Hosting Solutions, and I'll jump to that one. What we are. Total Web Hosting Solutions is a buy and build strategy in Europe, which we are buying hosting companies. My former company, PCextreme, was acquired by TWS in 2018. And now I am head of infrastructure, where we deploy Ceph and CloudStack using the KVM hypervisor. So a few things on a scale of what we work with is we have about 20,000 virtual machines, roughly 3 petabytes of Ceph storage, a lot of memory, and a lot of CPU cores. We have this running in data centers in the Netherlands, mainly in the Amsterdam area, in 3 data centers at the moment. It's all CloudStack and KVM. That's our target architecture, which we built on. Actually, tomorrow I have a talk about using CloudStack with VXLAN and BGP, so how we actually do the networking part. This time I will focus on the Ceph part. So if you have any questions during this talk, please ask in the chat or in the Q&A, because I have the chat open on a different window. So if you have any questions, do interrupt me and ask them. Otherwise, then I can answer them right away. So Ceph in a nutshell. It's a software-defined storage platform. It uses regular TCP/IP. You can either use IPv4 or IPv6. Well, you know, on my previous slide, you can actually guess on what we are using, but Ceph replicates your data over multiple nodes, or you can use Erasure coding, which you could call RAID over the network. You can have 2 choices. Replication is the fastest and the best one. It's the safest as well. However, it's the most expensive one. If you use replication 3x, which we use, then you have 1/3 of your raw capacity available as usable capacity. Well, Erasure coding, as I said, RAID over the network. In our case, we use EC4+3. You can compare it to RAID 6. However, RAID 6 has 2 parity drives. EC4+3, let's say RAID 7. And you can run Ceph on almost any hardware. The performance obviously is determined by the hardware which you use. Nowadays, you would see that most are using NVMe SSDs for their storage, but you can also use anything you like. You can run it on Raspberry Pis. Is it going to be fast? No. Does it work? Yeah, it works. Would you run it in production? No, but it's fun to test with, to play with at home. I'm not going to tell you in detail how Ceph works. If you want to know how Ceph works, or you get inspired by this talk, go to the Ceph website, learn more about Ceph. But this is the overview of Ceph in a nutshell. You have a few components with Ceph. We have monitors. We always need an odd number of monitors. What they do, they keep a track of the state of the cluster. So you always need 3, because 2 is not an odd number. 1 is an odd number, but there's no redundancy with 1. That's why we use 3 monitors at least. We have some larger deployments which use 5 monitors. The reason is, if you have a failure on Friday and you lose 1 monitor, you have 2 left. Well, do you want to go to the data center immediately to replace this monitor? Or can you say, well, if I have 5, I would have 4 left. I could wait until Monday to replace it. So that's a choice you can make. But if you deploy Ceph, at least you need 3 monitors. Then we have the managers, which collect statistics, run plugins. It's all written in Python, where you can have all kinds of plugins running to get the statistics out, sending to your influx database, Grafana, monitor disk health, etc., etc. But important to know, traffic will never go through the monitors nor the managers. So your data, your I/O will never go through those daemons. Because we have the OSDs, which are the object store daemons, they actually store the data. They have direct TCP/IP connections with the clients. In a CloudStack case, that would be the hypervisors, which they talk to, and the clients then directly communicate with them and exchange data. So the clients, they do talk to the managers to get the state of the cluster, but the actual data payloads go between the hypervisors and the OSDs. So that's Ceph in a nutshell, what it does and how we deploy it. However, we want to use Ceph as primary storage. It has been supported by the KVM hypervisor for a very, very long time. I actually haven't checked, but I think it has been since 2013 or 2014, quite some time now, and it works out of the box. If you have Ubuntu, CentOS, or if you would use Alma Linux now because CentOS is deprecated, it just works. Install libvirt, install the right packages, it works. And is it truly exciting? I wouldn't say. It's not that exciting anymore, but it's still very interesting. So it doesn't mean that it's boring now, so you shouldn't use it. No, boring is actually good in this case. It just works. The KVM implementation with Ceph primary storage works, and Ceph itself just works. So what we do is we deploy two flavors of Ceph clusters. We have those based on NVMe, which are actually just SSDs, but NVMe is just the interface. And we have those which are based on HDDs, and we use them for their own purposes. In our case, we mainly run web servers, mail servers, DNS servers, database servers. That's what we run as a hosting company. And we run all the production workloads from the NVMe systems. It's the fast storage for the workloads. However, we also have the HDD-based storage available in CloudStack, which is just used for archiving backup. For example, web servers which we have a second drive of usually 2 terabytes attached, which comes from the HDD-backed Ceph system, where we can create local backups. So if we have a backup, we can restore it very quickly from the local drive, which is based on HDD. So inside Linux, you'll just see a drive, which could be 500 gigabytes or a terabyte, which is the production data. And then there's a second drive, 2 terabytes or larger, where the backups go. In Linux, you can't see there's a difference between either NVMe or HDD, but performance-wise inside the VM, you'll notice. Now, both Ceph clusters, they use the same networking. So there's a top of rack switches running, all 10 gig. We experimented with 25 gig or more, but we're not usually bandwidth tight at the moment. So all the machines we buy from Supermicro and Dell, they still have 10 gig by default. So we just buy them with 10 gig. The latency of 25 gigs is slightly lower than that one of 10 gig, but we haven't noticed a real difference. So we're still using 10 gig in this case, and we might go to something other if we need it. Now, networking, IPv6 only, I'll get to that, and also to the top of rack switches, which are the gateways for all the Ceph servers, and they talk BGP. So there's no layer 2 in this network. So our SSD clusters, as again, I call them SSD because NVMe is just an interface. It's still a solid state drive, just using flash memory to store the data. Now, we use replication 3x. So if we would have 300 terabytes of raw capacity, that means we would have 100 terabytes of usable capacity. Now, we put it in one rack and we keep a Ceph cluster in one rack, so we don't scale out. So in one rack, you'll find 3 monitors, and then we fit in as much OSDs machines we can safely fit. Usually the power consumption in a rack is our limit, because a rack is 47 units in our case. Well, with 3 monitors, you would have 44 units left, some top of rack switches, some patching panels. We would be able to physically fit 35, 38 machines, but it doesn't fit power-wise because we have the power consumption restrictions, which is usually 5 to 6 kilowatts per rack. In our case, we can reach about 650 terabytes of raw capacity, well, divided by 3, roughly 210, 220 terabytes of usable capacity. That is 100% NVMe. Now, at the moment, we use the 4 terabyte NVMes. In these machines. However, we are thinking about switching to the 8 terabytes. Why 4 terabytes? Well, it's mainly about the failure domain. If we now lose a single machine, that's about 40 terabytes of raw capacity, which leaves the Ceph system. Ceph can handle it, but it's a bigger chunk which goes. If we would go to 8 terabytes, it would be 80 terabytes we would lose. We haven't really tested with it yet. We're still at 4 terabytes, but I'm pretty convinced you could run with 8 as well. Samsung has 16 terabyte. At some point you just need to say, this is the limit where I want to go safely. If you want to go to 8, you can go to 8. Our choice at the moment is going for 4 terabytes. And yes, we're using the AMD Epics, just best a price you can get for the performance they deliver. So it's all AMD Epic and some memory to run the OSDs on. 2 times 10 gigabits to the top of rack, and that's what we use, and just racks full of these machines running. So we use the same machines in all these clusters. We use a slightly older variant as well, the 113S instead of the 114S, but it's a mixture of those machines, which makes them interchangeable. So if we have we need some capacity, then we can just switch machines between the racks. And in the Q&A, I see a question. Yeah, so Samuel's asking something about the monitors. I will get to that question later because he's asking if you have using Ceph as a primary storage, can you add more monitors? Yes, you can. I'll answer the question right away. What we do is we have a DNS entry. So we're not using IP-based communication. We're not filling in the IP. We have a host name, and that host name simply has a round robin record pointing to the three monitors. So in our case, it would be, I think it's mon dot and then host name, which identifies the cluster. And if you looked at the DNS, we simply have three quad A records, which point to the 3 IPs of the monitors. And then in CloudStack, we provide the host name for the primary storage. And that's what we do. So there's no IP addresses in the CloudStack configuration. It's all DNS. And I hope that Samuel's question is answered by this. If we look at our HDD clusters, again, 1 cluster per rack, 3 mons, and again, as much OSD machines we can safely fit. We have about 2 petabytes of raw storage per rack with erasure coding and some safety margins. That's going to be 1.4 petabytes of usable storage. And this is used, as I said, for slow storage, for cold and archiving, backup storage. Slow storage could be, we have some people storing large amounts of large files. We just store them on the HDDs, which is much cheaper. In this case, we use some Dell machines. They just fitted this purpose better. So Dell R730 at the moment. 12 times 10 terabytes, and we have 2 times a 1 terabyte SSD for RocksDB offloading inside Ceph. I'm not going to go into RocksDB, but once you're looking into Ceph and how Ceph works, you'll find RocksDB and offloading of the BlueStore database. Well, that's why we use the 1 terabyte SSDs. And again, identical to the SSD clusters, there's 2 times 10 gigabit to the top of rack, which we are using for networking. Now, we use Juniper networking in our network mainly for the things where just static configurations used. So in this case, it's a QFX 5100 in a virtual chassis, and they route a /64 IPv6 subnet via BGP. In this case, you see a bit of configuration of IRB 180 in a virtual chassis, and IRB means the integrated routing bridge. It's a Juniper JunoOS configuration thing. We use an MTU of 9000 in this case, so jumbo frames, and the IPv6 subnet, and then semicolon 1. So it's the gateway for these Ceph servers. The Ceph servers themselves, they use LACP bonding, and they just get an IPv6 address, and they can be reached by the hypervisors. So for example, each of the racks have their own unique IPv6 subnet. So rack 1, rack 2, rack 3, we have, for example, 2 racks running with SSD storage, and then 1 with HDD. And based on the IPv6 subnet, we can actually see in which rack they are. So the /64 subnet will never leave that single rack. So based on the IP address and my IP administration, I know immediately in which rack that machine will be. So we're not stretching any VLANs over different racks. I go to Netbox, which we use for our data center administration. I fill in an IP address and it tells me, hey, this is going to be rack A05 in data center X. Oh, okay, nice. I know that because the configuration which we use just dictates that one IP can only be used, or one subnet can only be used inside one rack. So a drawing which we have of this case, one of our data centers in Amsterdam, one of the CloudStack zones, which is zone 03 AMS02, internal naming, you can forget it right away. At the left downside, you see that we have the CloudStack KVM hypervisors. They are all connected with 2 times 25 gigabits. something for tomorrow, because right now I'm focusing on the right side. The Ceph cluster part and the KVM hypervisors is something for tomorrow. But they're connected with, in total, 50 gigabits connected to some Cumulus Linux routers, which are then connected to other routers. And then eventually over 100 gig and 40 gig links, they can reach the Juniper QFX stack where the Ceph clusters are connected. And what you'll see is that the Ceph clusters, we simply replicate that. So if we need an additional Ceph cluster, we just built a new rack, 2 Juniper QFXs, a bunch of Ceph machines, BGP configuration, and we keep scaling out. So on this slide, what I mean is that we chose to not grow a Ceph cluster larger than a single rack. That's the entity which we see. It has a maximum capacity based on the size of the HDDs or SSDs. But we use this by preventing that if a single Ceph system goes down, although Ceph is very reliable, it can still happen. We prevent that the whole cloud environment goes down due to an issue with a single system. And we use the tagging of the storage tagging. So we have different disk offerings and service offerings, which make sure that different VMs use different Ceph clusters. And we can also do tiering with that. So we have disk offerings which say, hey, I'm going to be running on HDD. So there's going to be a tag HDD attached to the disk offering, and the Ceph cluster itself, the primary storage pool in CloudStack, has the tag HDD, which then means the volume will only end up on the Ceph clusters, which are HDD based, or otherwise around, the tag SSD means that the volume will end up on a Ceph system, which is SSD based. So in our data centers, you'll see multiple racks with hypervisors, multiple racks with Ceph systems, and they can either be SSD or HDD. So we do not have any scaling issues on the network. Layer 2 VLANs are never stretched anywhere in the network. Everything is layer 3 routed, all using BGP. And did we invent this ourselves? No, I wouldn't say stolen. We just looked at the hyperscalers on what they do. If you would look at Facebook, for example, you can have all kinds of opinions about Facebook on the company itself. But if you look at the engineering team from Facebook, they are guys which know what they are doing, and they have some very interesting papers on how they solved some scaling issues with BGP. And we looked at those, we learned from those, and we implemented many of those things in our network to make it future-proof. Because I've seen too many issues with scaling layer 2 over larger areas, or over racks. You had spanning tree loops, networks going down due to layer 2. So therefore, we are using layer 3 only, and we're building with IPv6 as well, because I would say IPv4, it's fine for the outside world, but internally IPv6 is so much easier because you have so much more IP space available. That's why we use IPv6 only, and it solves all kinds of other routing issues as well. And I see a question from Boris. Okay, what's the best feature of CloudStack that suits your infrastructure? How would you like to see CloudStack improve? I think that's actually one for the networking talk tomorrow, not for the Ceph part at the moment, because Ceph itself, I think that it's pretty mature with CloudStack at the moment. We can have some improvements about snapshots, where CloudStack works a bit better with the Ceph snapshots and actually leverages the features Ceph has with snapshotting. But networking wise, we can do a few things which can improve CloudStack. For example, right now, if users want to create an internal network themselves, we still need to provide a few things in VXLAN, and I would like CloudStack to provide that and a few routing issues. But I'll park that question for tomorrow, and that's actually will also maybe lure a few people of you into my talk for tomorrow. By getting back, it's all layer 3. There's no layer 2, and I would like to inspire people by thinking, hey, can I do this as well? And it's not that your network is going to be too small. You can do layer 3 everywhere. And there's also this thinking that switches are too slow for layer 3. Well, if you look at any modern switches, the Juniper QFX or Arista or Cumulus Linux, they are all fast enough to route layer 3 wire speed. Yes, that used to be a problem with the older chipsets years ago, but the newer chipsets, which are actually all Broadcom Tomahawk chipsets, they are fast enough to route this traffic. And then I see 2 questions I see from Rohit and Ray. I'll get to them in a moment. So Performance is, of course, always very interesting. And I mainly focus on write performance because we can talk about all kinds of read performance things and stuff, but in the end, writing and latency is what matters. Most applications benefit from fast writes. Reading is cached by the Linux kernel, applications themselves, or the storage system. It's usually pretty easy, but writing also takes time. Well, in the end, what we see is a 0.8 millisecond write latency. I did some recent benchmarks where I could go to 0.6.5, so going a bit lower. So I always test with a 4K write size, a queue depth of 1, and 3x replication. Because replication is the fastest and it's also the safest. Yes, people might say, let's go for 2x replication. Well, if you just go on internet and look for the 2x replication stories with Ceph, it is horrible. You are guaranteed to lose data at some point if you start scaling out your Ceph systems. So never use 2x replications. And we have the CPUs on the performance profile with the C state pin to 1. And the latter really matters. So C state pinning to 1, that really helps with your Ceph performance. It actually also helps with your hypervisors. All our hypervisors are pinned to C state 1 and the performance profile of the CPUs. And we see that it really benefits, in our case, the performance of the I/O. But inside web servers, for example, the parse time of PHP, so the time to first byte of a website is really going up with pinning a CPU to C state 1. So again, a 4K write in about 0.8 milliseconds of a write size. Now, I've seen questions on the mailing list on how can you use erasure coding with CloudStack, because there's a few things which you need to think about. When creating a pool, a primary storage pool in CloudStack, you can only give in one pool with Ceph, and with erasure coding, you actually need 2. You need a small replicated pool, which is the index pool, and then you need a data pool. Well, if you look at the screenshot here of one of the systems, I took the screenshot earlier today. It has 2 pools, actually 3, but we can ignore the device health metrics pool. We have an RBD pool. As you can see, there's 205 megabytes of data stored in here. It's just an index pool, so it has some metadata about the volumes in there. But the actual data is in the RBD-data pool, which is at the moment 365 terabytes of used capacity in that pool. So it's at near 80% at the moment in that pool. That's actually the data pool. So we have the index pool RBD, the RBD data pool, which is the data pool. So how do you configure this inside CloudStack and Ceph? Well, you add the primary storage in CloudStack using the pool RBD, the index pool. That's what you refer to. However, inside the Ceph configuration, you need to make sure that you set the RBD default data pool configuration to RBD data. The example is shown here, which command you need to execute, and then the result it needs to have. So clients, because this is all done by the Ceph clients, they will then know that they need to store the actual data in the RBD data pool. And then we have a dump of the OSD map in Ceph, where you see that pool 2, the pool RBD, as a replicated pool with a size of 3, size meaning the amount of replicas, and the erasure profile is called EC4+2. And actually the profile, that's a typo because we use 4+3, but I think in this case, but it needs to be EC4+3. But it's using erasure coding, and this way we store the data in erasure coded pool. Again, only being used by slow archiving and cold storage. So performance, don't expect any high performance from erasure coding, especially we're using 10 terabyte drives. We could have going higher to 12 or to 14, 16, 18. We're not going there yet because the recovery times just go up. The speed of the disk, the performance of a single disk doesn't go up if you go to a larger drive. So the recovery times simply keep getting higher and higher and higher. We don't dare going over 10 terabytes at the moment. Maybe we'll do in the future, but right now we say that 10 terabytes is okay. I've seen a disk fail, I think 2 weeks ago, and the rebuild time was 26 hours for a single drive. And you can say, Ceph is slow. Well, it's just a lot of data which needs to be copied, and those drives are just slow because you need to think that you're not only recovering, but you're also still serving the active I/O, and that's where HDDs are just too slow. But what I do recommend is setting I/O limits on your disk offerings, and we mainly write a limit on the write I/Os. We limit to 250 IOs per second. write IOPS, and I think to 100 megabytes per second. That's what a single VM can write. Otherwise, you can have a single VM quickly overloading your Erasure coded cluster because it just overwhelms the system with IO. So what you see with Erasure coding is that the price per terabyte is low, but the price per IO is very high. And with an SSD cluster, it's the way around. So there the price per terabyte is high, but the price per IO is lower. I wouldn't say low, but it's lower. So that's where you need to choose. You can't have both. You can't have fast performance or high performance and low price. You know, that doesn't match. That you need to sacrifice something. And that actually brings you to the end of my talk, but I do see some questions from Rohit. Rohit, Ray, and Justin asking questions. So Rohit is asking, how are Ceph upgrades? Easy, hard, nail biting, any upgrade stories to share? Pretty easy. You, as always, read the release notes and then simply start doing the upgrade. With Ceph, however, you need to think that the client is actively participating in the Ceph cluster. So when upgrading Ceph, you also need to upgrade the packages on your hypervisor, and then you would either need to restart the VM, actually stop the VM or start it, or do a live migration of the VM to a different hypervisor. So it's a bit of a work, but if you automate this with Ansible or Puppet or whatever you use, it's pretty easy. You upgrade the Ceph system to the latest version without any downtime. So that's actually pretty nice. And the cool thing with Ceph as well, you can just mark what we call out a machine, and then it goes out of production, and you can replace machines, move complete workloads to different racks, etc., without any downtime of the actual data. So that's really the main benefit about Ceph is it's very flexible. I could set up a new rack with new machines, shift all my data to the new rack while all the applications which are running in front are still running, and then I can just decommission the old hardware in a rack. We're not there yet because all the hardware is within the 5-year period, but I'm thinking about this, how we're going to do this in 2 years, 3 years, and then we'll simply install new racks with new hardware, and we move the whole Ceph cluster to a new rack, and then we can decommission the old hardware. So I try to avoid doing maintenance inside a single rack. A rack serves a purpose. We rack it once. Then it does its job running for a few years, and then we move all the workload to a different rack. We empty the rack, new hardware goes in. That's how we recycle. I've seen that doing maintenance inside a single rack usually makes the spaghetti. All the cables becomes a spaghetti. It's a nightmare. But of course, you need to have a bit of scale to do so. And the question for Ray: how would you advise Ceph clusters for relatively small and below clouds? 50 terabytes honestly is on the low side with Ceph. If you look at the price per terabyte, 50 terabytes with Ceph, it's not going to work out for you. You do get the flexibility of Ceph and all the cool features it offers with the flexibility of moving and shifting to other hardware pretty easily. And you know, the turnkey solutions from Dell or HP, yes, they work really well, but do keep in mind you have a vendor lock in there. So if the vendor prices go up with them, you're stuck. And or if they declare the product end of life, you need to migrate to something else. That's a flexibility Ceph offers you, but with 50 terabytes, you'll be looking at a pretty high price per terabyte. I would usually say that Ceph starts making sense from 250 to 500 terabytes of data. And then 2 questions from Justin. Do we use RDMA? No, we don't use RDMA. That's simply not production ready with Ceph at the moment, so it's all TCP/IP. Pretty interesting RDMA. We have the Mellanox cards in our hypervisors, which also supports RDMA, but we use them for VXLAN offloading at the moment. Would be interesting, not at the moment. And then the question, what base OS we're using, it is all Ubuntu 20.04 in our case. And we might be going we'll be going to 22.04 in April, and we probably still have a few old machines running 18.04. Okay, so yeah, Rohit and Ray, you're welcome for the answer. I see that in the chat. No other questions at the moment. I'll go back to one more thing is that, yeah, so the reason we have Supermicro and Dell, it's mainly we do a balance between the two vendors. So if Dell has a good offer, we'll go for Dell machines. If Supermicro has a good offer, we'll go for Supermicro. But here again, we stick to one vendor in one rack. So we have Ceph clusters running with Dell machines as well, but then you'll see a whole rack full of Dell machines running a Ceph cluster, and the other rack is Supermicro. We don't mix within the racks to keep the racks clean and functional and easy to maintain. But again, I do understand this is because we have a certain scale which we can operate on, which makes it easier for us. Okay, well, that actually brought me to the end of my talk. I don't see any additional questions. Giles, you have anything to add?
No, not at all. Just to say thank you, Wido. Really enjoyed that talk. I think by the look of the chat
one
here.
Coming in.
Oh,
Wei is asking, how much is the 10 times 4 terabyte NVMe? At the moment, but you know, chip shortage, it's getting difficult at the moment for this machine. Let me go there. I think the prices we pay about 10 to 11,000 euros at the moment for such machines. They used to be lower, in the 8 to 9,000 euro range, but prices have been going up for the CPUs, memory, and the NVMe's. I see Michael asking a question as well about not 8 terabytes, it's failure domain. Right now, I would lose a machine which has 40 terabytes, then I would lose a machine which is hosting 80 terabytes. And with failing, we always say, the machine might break, but we also want to have the flexibility to take a machine out for maintenance. So if I now shut down a machine, I take away 40 terabytes of capacity, which is okay, but otherwise I would take away a machine with 80 terabytes of capacity. And that could be OS upgrades, because we tend not to upgrade the OS, but just to reinstall with a newer version, just to have the machines clean again. And at the moment, we say that if we have a full rack, we can tolerate the loss of 40 terabytes, otherwise we would have to tolerate the loss of 80 terabytes. But technically, you could use the 8 terabytes.
Any more questions for Wido? You've covered everything, Wido.
Yeah, I think so. And
Great.
Otherwise, at the last part, there is my email address. So if you have any other questions, feel free to send me an email. One more question from Sebastian. Is 2 times 10 gigabit enough? Yes. What we see is, although NVMe can push more than the 20 gigabits, we don't see that much traffic going through. We mainly see I/O, but in our workload, it's very small I/O. So usually we see that those systems are doing, I would say, full cluster is doing about 100,000 IOPS, so 100,000 IOPS per second, and the total bandwidth is, for the whole cluster, the total bandwidth 4 or 5 gigabits. What we see in traffic. So no, with recovery, we do see that machines are, so the whole cluster goes up to 40, 50 gigabits for the whole cluster when recovery is happening. But there's no added value for us right now to go to more than 10 gigs. It's not really needed in our workload.
Okay. Any more questions? Any more?
Okay. No, I see Rohit looking forward to the networking talk. So I'm going to keep that for tomorrow, about talking about VXLAN, BGP, IPv6, EVPN, interesting stuff on how we scale out our network behind the hypervisors.
Brilliant. Well, last thing then, just to say thank you, Wido. Really great talk. Everybody, please give Wido a big virtual round of applause for his talk. Thanks, Wido.
Okay, you're welcome. Thank you. And I hope to see you guys tomorrow.